You've found Dreamtime Science, part classroom, part lullaby, entirely devoted to satisfying your curiosity while you find your way to sleep. You know, I've been thinking about how warmth from a cup of tea slowly drifts into the chilly air, and there's something really remarkable about why energy never seems to stay put. It's like the universe has this quiet habit of spreading heat around, and understanding that tells us so much about how the world gently balances itself. I'm excited to share with you the simple yet surprising ways physics explains this peaceful flow of energy tonight. Should these dreamy explorations accompany your journey to sleep, a gentle like or subscription would be deeply appreciated. What questions about our universe keep you wonderfully curious? Before we begin, create your sanctuary, nestle into your chosen spot, let your muscles soften, and allow your breath to find its natural rhythm. Heat. The word itself is almost an incantation, a whisper of comfort or a warning, depending on the mood of the day and the stories we carry with us. It may conjure visions of gentle sunlight spilling through a childhood window, or the shuddering, invisible wave that ripples off the hood of a car in midsummer. Perhaps for you, it's the sharp crackle of a campfire, or the heavy, oppressive embrace of a humid afternoon. Yet, beneath all of these experiences, behind the poetry and the memory, there lies a hidden truth. Heat is not a thing, but a process, a movement, a ceaseless transformation that binds the universe together in ways both subtle and profound. To truly appreciate the essence of heat, one must first untangle it from the misconceptions that have long woven themselves into our culture and language. For centuries, people imagined heat as a kind of substance, an ethereal fluid, sometimes called caloric, that could be poured from one object into another. This is not so strange when you think about it. After all, when you touch a warm mug, it feels as though something flows into your hand, a tangible presence. In this old view, heat was a material, a stuff, as real as water or air, and this notion persisted well into the age of steam and industry. Yet, as our understanding deepened, as clever experiments teased apart the secrets of nature, a new perspective emerged. Heat, we learned, is not a material at all, but a form of energy, one that slips quietly from place to place, always seeking equilibrium, always smoothing out the jagged contours of temperature and motion. It is, in essence, the restless dance of molecules, the jostling and vibrating and colliding that fills every piece of matter in the cosmos. Where there is heat, there is motion, sometimes wild and chaotic, sometimes gentle but always present. Consider for a moment a scene from a film, perhaps one that has etched itself into the cultural imagination, the world in crisis, the climate gone awry, as in The Day After Tomorrow. In that cinematic vision, heat is a character, a force to be feared, harnessed, or lost. The cold sweeps in, monstrous and sudden, as if the very spirit of warmth has been banished from the earth. People huddle together, desperate for shelter, for the flicker of a flame, for the reassurance that life, in all its vulnerability, can persist against the dark. In such stories, heat is more than physics. It is hope and peril, a symbol of both destruction and survival. Yet, outside the realm of fiction, the reality is stranger and more beautiful. Heat is impartial. It has no malice, no agenda. It is simply the way the universe redistributes its energy, the manner in which the cosmos strives for balance. When you light a match, you are not summoning fire from the ether, but unleashing the stored energy of chemical bonds, allowing atoms to rearrange themselves, flinging their motion outward. The warmth you feel is the evidence of this microscopic tumult, a shivering at the smallest scale made manifest on the skin. This is the secret language of heat. Every warm object, every cup of tea, every sunlit stone, every body at rest, is a symphony of particles in motion. Imagine peering into the heart of matter itself, diving deeper and deeper until the familiar world dissolves into a blur of atoms and molecules. What you would see is not stillness, but frenzy. Molecules vibrating, tumbling, spinning, ricocheting off one another like tiny billiard balls, their movements governed by the invisible hand of energy. This internal motion is the essence of temperature, and heat is the process by which this motion is shared, borrowed, and exchanged. It is tempting to think of heat as something you can possess, like a coin or a keepsake, but heat is slippery, always on the move. It flows from regions of higher temperature to those of lower, not because it is forced to, but because nature abhors imbalance. If you place an ice cube in a glass of water, the chill does not seep outward. Rather, the warmth of the water migrates inward, agitating the rigid lattice of the ice, coaxing it to melt. The universe, at every scale, is engaged in this subtle negotiation, always tending toward equilibrium, always leveling the differences. This drive for balance is woven into the fabric of existence. It is why your breath fogs in winter, why the desert cools so swiftly at night, why a fever feels like a battle waged beneath the skin. In every instance, heat is energy in transit, slipping across boundaries, seeking a kind of peace. And yet, this peace is never perfect, never complete. The universe is too vast, too restless, to ever settle entirely. There will always be gradients, always regions where energy pools or ebbs, waiting to be shared. Think again of the stories we tell, the apocalyptic visions of a world frozen or aflame. In The Day After Tomorrow, disaster is framed as a sudden absence of heat, a catastrophic reordering of the climate that leaves cities encased in ice. The spectacle is thrilling, but it also hints at a deeper truth. Our lives, our societies, are built on the management of heat. We crave warmth in the cold, relief in the heat, and we have devised 1,000 ways to bend this energy to our will. Fires, furnaces, engines, air conditioners. Each is a testament to our desire to shape the world, to carve out islands of comfort and safety in the vast, indifferent sea of nature. Yet, for all our ingenuity, we remain at the mercy of heat's quiet power. We are creatures of temperature, our bodies finely tuned to a narrow range, our cells and enzymes delicate instruments that depend on just the right amount of molecular jostling. Too much heat, and proteins unravel, systems fail. Too little, and the machinery of life grinds to a halt. This is why fever alarms us, why hypothermia terrifies. It is a reminder that heat is not just a backdrop to our lives, but a participant, a force that shapes our fate moment by moment. But let us set aside the drama of disaster and linger instead on the gentle ubiquity of heat. It is all around us, in every breath, every heartbeat, every ray of light that filters through the atmosphere. Even in the coldest reaches of space, where the night is eternal and the stars are distant, there is still a faint warmth, a residue of the Big Bang itself. The cosmic microwave background, a whisper of heat from the birth of the universe, pervades all of existence, a silent testament to the primordial fire from which everything arose. Here on Earth, heat is the engine of change, the wind that stirs the leaves, the currents that churn the oceans, the cycles of weather and climate, all are driven by the sun's radiant energy, streaming across the void, absorbed and re-emitted, scattered and transformed. The sunlight that warms your face on a spring afternoon is ancient. Its journey began in the heart of the sun, where atoms fused and released energy that took tens of thousands of years to reach the surface, and only then did it leap across space to touch your skin. In that moment, you are bathed in the afterglow of nuclear fire, the beneficiary of a process as old as time. This relentless exchange of energy is what allows life to flourish. Plants drink in sunlight and turn it into sugar, storing the sun's heat in the bonds of carbon and hydrogen. Animals, in turn, consume these stores, breaking them apart, releasing the captured energy as heat once again. The cycle is endless, a perpetual dance of capture and release, storage and dissipation. And at every stage, heat is both the currency and the cost, the price we pay for motion, for thought, for life itself. We often forget this, distracted as we are by the visible, the tangible. We notice the flame, but not the chemical ballet that feeds it. We feel the warmth, but not the frantic vibrations that create it. Yet, if you close your eyes and listen, not just with your ears, but with your mind, you can almost sense the ceaseless murmur of heat, the way it threads through every moment, every object, every living thing. It is the pulse of the world, the background hum of existence. Culturally, heat has always been more than just a physical reality. It is a symbol, a metaphor, a source of myth and meaning. Ancient peoples worshipped the sun, built rituals around the solstices, told stories of fire stolen from the gods. In literature, heat is passion, anger, desire, a force that consumes and purifies. Even today, we speak of warmth in our relationships, of fiery tempers, of chilling fears. These are not mere coincidences, but echoes of a deeper truth, that heat, in all its forms, is central to our experience of the world. Yet, for all its familiarity, heat remains elusive, difficult to pin down. It is not a substance you can hold in your hand, not a thing you can see with your eyes alone. It is an event, a transfer, a consequence of motion and interaction. The warmth of a blanket on a cold night is not magic, but physics, the slow migration of energy from your body, through the tangled fibers, into the air. The shiver that runs down your spine on a frosty morning is a message from your nervous system urging you to move, to generate more heat, to preserve the delicate balance within. And so, as night falls and the world grows quiet, heat becomes something intimate, almost sacred. It is the memory of the day, lingering in the stones and the walls. It is the comfort of a shared bed, the closeness of another body, the reassurance that even in the darkness, energy persists. In this way, heat is both a mystery and a constant companion, a gentle reminder that beneath the surface of things, the universe is always in motion, always exchanging, always alive. If you listen closely, you can hear the old misconceptions still echoing, the idea of heat as a substance, a fluid, a thing to be transferred. But now, with the wisdom of science, we see more clearly. Heat is energy, pure and restless, always seeking to even out the disparities of the world. It is the bridge between order and chaos, the architect of change, the silent force that shapes mountains, carves rivers, and sustains the fragile miracle of life. As you drift deeper into this night, perhaps you will feel the warmth of your own breath, the gentle glow that radiates from your skin, the slow, steady pulse of energy that connects you to the world. It is not just comfort. It is the story of the universe, written in the language of motion and exchange. And somewhere, far beyond the reach of sight or sound, this same energy is at work, swirling in the stars, whispering through the void, waiting to reveal its next secret. In the quiet of the night, as the world slips into shadow and silence, there is a curious paradox at the heart of the universe's restlessness. For even when every field and meadow appears stilled, every star seems locked in its distant, glittering place. Something deeper and more intricate is always unfolding, a ceaseless, subtle, and chaotic dance of energy. This is not the chaos of violence or destruction, but a far more profound and fundamental shuffling, the intricate ballet of thermal motion, choreographed by the laws of nature, and yet, at its heart, unpredictable in the details. Let us slow our thoughts to the pace of this underlying world, where every atom and molecule is an eager dancer, and every fleeting collision marks a step in an eternal waltz. Here, the air in a quiet bedroom is as lively as a teeming city, though its commotion is too small and swift for our senses to grasp. Each molecule of nitrogen and oxygen ricochets and twirls, their motions a blur of randomness. If you were to shrink down, becoming as small as a single air molecule, you would be swept along in a storm of collisions, your path zigzagging in a wild and unpredictable frenzy. This apparent disorder is not lawless. On the contrary, it is governed by principles as strict as those that guide planets in their stately orbits. The second law of thermodynamics, that stern, unyielding directive, whispers the rules into the ears of every particle. Energy must spread, temperature must even out, and disorder, entropy, must always increase or, at best, hold steady. The universe demands that heat flows from warm to cold, never the reverse, and that any local patch of order comes at the expense of greater disorder elsewhere. Yet, to truly appreciate the subtlety of this law, we must linger a while on the nature of entropy itself. The word is soft, almost gentle, but what it carries is the weight of inevitability. In its most basic sense, entropy is a measure of the ways a system can be arranged, the number of microstates consistent with its macrostate. If you imagine a deck of cards lying in a neat, ordered stack, there are few ways for the cards to sit, but if you shuffle them, the number of possible arrangements explodes. The entropy rises. The system, once ordered, has become more disordered. In the physical world, the microstates are the positions and velocities of all the particles. When energy is confined, tightly packed, there are few arrangements. When it is free, spread out, the possibilities multiply. This is the law that guides the spread of warmth from a mug of tea into the cool air, the mixing of cream into coffee, or the slow, inexorable cooling of stars. The energy, always restless, always seeking the widest pastures, drifts from where it is concentrated to where it is sparse. And in this drift, this mad scramble for new arrangements, entropy surges. But how does this chaos emerge from the order of physical law? How does the ticking of time, so precise in the equations of Newton and Schrödinger, give rise to the one-way drift of heat, the asymmetry that makes the past so different from the future? It is here, in the heart of this question, that the true mystery of thermal chaos reveals itself. For at the level of the most fundamental laws, those that govern the dance of particles and the undulations of fields, there is no preferred direction of time. The equations work as well in reverse as they do going forward. And yet, in our lived experience, the egg never unstirs, the tea never flows back into the kettle, the warmth never leaps from the cold night air back into the mug. The answer, as physicists have come to understand, lies in the sheer number of possibilities. Imagine a box divided in half by a wall with all the air molecules on one side. When the wall is lifted, the molecules spread, filling both halves. The odds of every molecule spontaneously retreating to their starting side are so vanishingly small as to be indistinguishable from impossible. It could happen, but you would have to wait longer than the age of the universe to see it. Thus the arrow of time is born from probability, not from any ironclad law. The universe does not forbid order from arising, it simply makes it so unlikely that for all practical purposes it never does. This is the heart of entropy, not a force nor a field, but a statement of unlikelihood. The universe, vast and sprawling, prefers the ordinary over the extraordinary. The shuffling of particles into disorder is simply more probable than their lining up in neat rows of structure. And so the world drifts, one moment to the next, always toward the broad plane of higher entropy, where the possibilities are richest and the patterns most diffuse. It is tempting to see this as a kind of cosmic pessimism. Indeed, stories have been told of the so-called heat death of the universe, when all energy is spread so thin, so evenly, that nothing more can happen. No structure can arise, no thought can flicker into being, a future of infinite sameness, where entropy has claimed its final victory. This idea, popularized in the 19th century and echoed in countless tales since, casts a long shadow. It is the ultimate dusk, the cooling of all cosmic fires, the end of all story. But is it truly so bleak, or even so certain? Here the limits of our understanding begin to show themselves, like the faint lines of a map fading into uncharted territory. The universe, it turns out, is more subtle than our first imaginings. Entropy is not a simple tally of disorder, nor is heat-death a single, inescapable fate. The story is richer and far stranger. For example, not every increase in entropy is the same. The entropy of a black hole, that most enigmatic of cosmic objects, is vast, so vast, in fact, that it dwarfs the entropy of ordinary matter by orders of magnitude. The surface area of a black hole's event horizon, not its volume, sets its entropy, defying our everyday intuition. And in the early universe, when everything was hot and dense, entropy was surprisingly low. As the universe expanded, the entropy grew, but so too did complexity. Stars formed, galaxies spun into being, planets cooled, and chemistry blossomed into life. Even now, on our own small world, local eddies of order emerge, life, thought, art, fed by the gradients of energy pouring from the sun. The Earth basks in low-entropy sunlight and emits higher-entropy infrared light, using the difference to build forests, oceans, and civilizations. Life does not defy the second law. It dances within its constraints, shuffling the deck in ever more elaborate ways. And here, perhaps, we find the thread that winds through the heart of Vonnegut's Cat's Cradle. In that story, entropy is not just a scientific concept, but a metaphor, a symbol of futility and inevitability. The fictional substance, Ice 9, is a crystalline form of water, a seed that once introduced could freeze the world's oceans in a single, irreversible cascade. The myth of Ice 9 is the myth of inescapable change, of the sudden unmaking of order. But entropy, in reality, is not so abrupt. It is a slow seep, a gentle drift, a rearrangement that, while it brings a kind of dissolution, also gives rise to new forms. Ice 9, if it existed, would indeed bring a catastrophic increase in order, a world locked in crystalline symmetry, every water molecule snapped into place. But such order, paradoxically, is also a kind of death. For in perfect order there is no room for the dance, no motion, no heat. Entropy, for all its reputation as the herald of decay, is also the wellspring of possibility. Without it there can be no change, no mixing, no life. The intricate dance of thermal chaos is not just the story of how things fall apart, but also of how they come together, how they move, how they live. Yet as we peer deeper into the heart of this dance, questions arise that even the sharpest minds cannot yet resolve. The universe, it seems, had a beginning, a moment when entropy was at its lowest, when order reigned supreme. Why should this be? Why should the cosmos have begun in such an unlikely state, poised on the edge of a vast plain of possibility? And if entropy must always rise, what then of the far future? Will the universe truly drift into silence, or will new forms of order emerge, unpredictable from our vantage point among the stars? Modern physics, for all its precision, offers only partial answers. The equations of quantum mechanics, of general relativity, and of statistical mechanics describe the rules of the dance. But why the dance began, and what steps it will take in the end, remains obscure. Some theories suggest that new universes might bud off from our own, each with its own arrow of time. Others hint that information, the true currency of entropy, might be preserved in ways we do not yet grasp, hidden in the tangled mathematics of quantum gravity. We are left then with a paradox at the heart of our understanding. Entropy is both the limit and the source of creativity. It is the measure of what can happen, not just what must. The universe, sprawling and ancient, does not simply wind down like a tired clock. It explores, it rearranges, it surprises. The intricacy of thermal chaos is not a sign of despair, but of exuberant variety. As you drift, listening to the whispers of air and the gentle hum of distant stars, consider that in each moment, even in the depths of night, you are enfolded in this ongoing dance. The warmth of your breath, the slow cooling of the day, the silent shuffling of atoms in your bones, these are all threads in the larger tapestry. The boundaries between order and disorder are not walls, but thresholds, crossed and recrossed in every heartbeat, every flutter of thought. And so, the myth of heat death remains a story, compelling but incomplete. The universe is not a static stage, but a living performance, its script unwritten and its choreography ever-changing. Entropy is not the enemy of meaning, but its canvas, the broad field upon which all possibility is drawn. The dance of thermal chaos continues, unhurried and inexhaustible, carrying us forward into the unknown. In the next phase of our journey, the question lingers: how do the patterns of energy and entropy, so discernible in the stars and in the spaces between, shape the emergence of complexity and structure? What hidden symmetries and secret languages guide the birth of galaxies, the swirl of hurricanes, the spiral of seashells? The answers lie not in the silence of heat death, but in the persistent, restless creativity of the universe itself. If you listen closely, you can almost hear it. The faint ticking of a clockwork world, each second marking the passage of heat from one substance to another. Heat is a restless traveller, seldom still, always seeking an evenness it never quite achieves. For centuries, humans sensed its presence only in the warmth of sunlight on stone, the bite of frost in winter, or the flush of fever. But to truly understand its restless journey, to tame the invisible tides of temperature, we needed more than sensation. We needed instruments, experiments, and a language to describe what we could not see. This is the thermometer's tale, a story of glass and mercury, of explosions in laboratories and revelations in darkened rooms, of the clever minds who chased the secrets of heat across the centuries. Long ago, there were no numbers for warmth or cold. People knew only what their skin could sense. A day was hot or cool, water might scald or chill. No one could say, with certainty, whether a fever burned higher today than yesterday, or whether the forge was truly hot enough for the smith's task. Only crude comparisons were possible, and even those bent under the weight of subjectivity. The journey to clarity began, as so many journeys do, with a question. Could the elusive quality of heat be measured, assigned a value, made real in the realm of numbers? The first steps were tentative. In 1592, Galileo Galilei, the Tuscan polymath who watched the heavens with a homemade telescope, turned his attention earthward. He fashioned what he called a thermoscope, a simple glass tube sealed at one end with a bulb at the other. He filled the bulb with air, inverted the device into a vessel of coloured water, and observed what happened as the surrounding air warmed or cooled. When the air in the bulb expanded, it pushed the coloured water down the tube. When it contracted, the water rose. Thus, the thermoscope translated the dance of air molecules, unseen, unknown then, into motion visible to the human eye. It could not assign numbers, nor could it compare one device to another. But for the first time, the ephemeral quality of warmth could be recorded, however crudely, outside the body's own unreliable senses. This was a beginning. Others built upon it, refining the design and the dream. 17th-century inventors, scattered across Europe, crafted their own thermoscopes. They filled their bulbs with spirits or wine, learning that liquids responded more reliably than air. As glass blowers shaped ever finer tubes, the idea of creating a universal measure began to take hold, a scale of temperature that anyone, anywhere, could use. But the world was not so simple. Air pressure changed with the weather, and with it the readings of early thermoscopes flickered and failed. It was a Dutch scientist, Christian Huygens, who in 1665 first suggested sealing the tube and using mercury, a silvery liquid metal, as the measuring medium. Mercury, dense and quick to respond, did not cling to glass or freeze easily. in the hands of Daniel Gabriel Fahrenheit, the German-Polish physicist working in the early 18th century, the mercury thermometer at last achieved both precision and portability. Fahrenheit devised a scale, arbitrary perhaps, but reproducible. He set 0 at the coldest brine he could concoct, fixed another point at the freezing of water, and yet another at the warmth of the human body. With this, the world gained its first reliable temperature scale, and the language of heat grew richer. Yet Fahrenheit was not alone in seeking order. Anders Celsius, in Sweden, proposed a scale in which the freezing and boiling points of water marked the ends, 0 and 100, a system as elegant as the snows of his homeland. Lord Kelvin, in time, would offer a scale that began at absolute 0, the coldest conceivable state, where all molecular motion ceases. The thermometer, once a curiosity, became a bridge between worlds, uniting the sensations of flesh with the precision of mathematics. But measuring heat was only the beginning. What, after all, was heat? Was it a substance, a fluid, a weightless caloric that flowed from hot to cold? For decades, scientists imagined heat as an invisible liquid, seeping from one object to another, much as water trickles through soil. This notion, the caloric theory, shaped early experiments and explanations. It was a world where heat could be poured, stored, or trapped, where the fires of chemistry and the engines of industry drew upon an unseen reservoir. The flaws in this picture were subtle, stubborn. The Scottish physicist Joseph Black, in the mid-18th century, began to probe the mysteries of phase change. He noticed that when ice melted or water boiled, heat vanished, yet the temperature remained constant. Where did this latent heat go? Black's careful experiments suggested that heat was not a single substance, but a form of energy. It could be hidden, bound up in the transformation of solid to liquid or liquid to vapor, without raising the temperature at all. The thermometer's tale grew more complex, tracing not just the rise and fall of mercury, but the hidden highways of energy itself. As the Industrial Revolution thundered to life, heat became more than a curiosity. It was the beating heart of engines, the force that drove pistons and spun wheels. Yet the engines of the early 19th century were wasteful, leaking energy at every turn. A French engineer, Nicolas Léonard Sadi Carnot, sought to understand why. In the flickering light of his study, Carnot imagined an ideal engine, one that wasted nothing, that harnessed every bit of heat to do useful work. He realized that no engine could be perfect. Some heat would always slip away, lost to the chill of the surroundings. Carnot's insights, published in 1824, became the seeds of thermodynamics, the science of heat and work, of engines and entropy. But it was James Prescott Joule, an English brewer's son with a taste for precision, who dealt the final blow to the caloric theory. In the 1840s, Joule set out to prove that heat was not a substance, but a form of motion, a manifestation of energy in transit. His experiments were marvels of care and ingenuity. He built a device in which falling weights spun paddles submerged in water. As the paddles churned, the water warmed. Joule measured the temperature rise with a thermometer, now a trusty companion in every experiment, and calculated the energy lost by the falling weights. Again and again the numbers matched. Mechanical work could be transformed into heat, and the amount was always the same. Joule's results were met with skepticism, even derision. Yet he persisted, refining his apparatus, eliminating errors, and publishing his findings. Eventually, the scientific world could not ignore the evidence. Heat and work were two faces of the same coin. Energy, conserved and exchanged, never created nor destroyed. The first law of thermodynamics emerged from Joule's persistence, forever linking the rise of the thermometer with the fall of old ideas. Another visionary, Lord Kelvin, born William Thomson, took these revelations further. Kelvin understood that if energy was conserved, then there must exist a lowest possible temperature, a place where all molecular motion ceased, where no further energy could be extracted. He calculated this absolute zero to be minus 273, 15 degrees on the Celsius scale. From this insight, Kelvin crafted a new temperature scale, beginning at this cosmic chill. The Kelvin scale became the standard for scientific inquiry, its 0 point a horizon, beyond which nothing could go. The thermometer, now graduated in kelvins, could measure not only the warmth of tea or the heat of a furnace, but also the faint flicker of cosmic cold in the depths of space. With these tools, the science of heat leapt forward. The laws of thermodynamics, discovered, refined, and debated by generations of thinkers, offered a framework for understanding engines, the growth of crystals, the melting of ice, and even the fate of the universe itself. The humble thermometer, once a curiosity, became a symbol of the quest for order in a world of restless energy. Yet the thermometer's tale did not end with glass tubes and liquid metals. In time, new technologies emerged, each more sensitive, more probing, more attuned to the hidden world of heat. The 20th century witnessed the rise of thermocouples, wires of two different metals fused together at one end. When heated, they produced a tiny electric voltage, a subtle signal that could be amplified and measured. Thermistors and resistance temperature detectors followed, exploiting the way electrical resistance changed with temperature. These new instruments could reach into places unreachable by glass, the hearts of engines, the depths of oceans, the distant atmospheres of planets. And then, as our understanding of light deepened, another revolution unfolded. Every object, no matter how cool or hot, emits a faint glow, infrared radiation, invisible to the eye, but real as any sunbeam. Scientists learned to build detectors sensitive to this hidden light. With thermal imaging cameras, we saw the world anew, the heat of a handprint fading from a wall, the living warmth of animals in the darkness, the fevered blush of disease invisible to ordinary sight. Infrared telescopes peered into the coldest reaches of space, mapping the afterglow of creation itself. Yet, for all these advances, the challenges of studying heat remain as subtle as ever. Heat is not a thing, but a process, a ceaseless migration of energy, always slipping from order to disorder, from hot to cold. Its measurement is an act of translation, the chaotic jostling of atoms rendered at last as a reading on a dial or a splash of color on a screen. Each instrument, whether of glass and mercury or silicon and gold, tells part of the story. None can capture it all. Still, the quest to understand heat and its workings continues. In carefully controlled laboratories, scientists watch the dance of single atoms, measuring temperature shifts so small they defy belief. They probe the quantum world, where energy comes in packets, and temperature becomes a whisper, a probability, a hint. They dream of engines that waste nothing, of materials that conduct or insulate with exquisite precision, of a deeper order hidden in the apparent chaos. And always the thermometer stands as witness, a slender artifact of human ingenuity and curiosity, a bridge between the tactile world of sensation and the abstract realms of energy and entropy. Through glass, through wire, through photon and electron, it tells us where heat has been and where it is going. It reminds us that even in the most ordinary moment, a cup of tea cooling on a windowsill, a child's fever measured with gentle concern, we are participating in the grand adventure of thermodynamics, the ongoing effort to understand the restless, relentless, and beautiful journey of energy through the universe. But the story is not yet complete. Beyond the numbers and the scales, beyond the tools and the tales, lies a deeper question. What does heat truly mean for the world around us? How does it shape the patterns of weather and life, the flow of rivers and the beating of hearts? As the night deepens and the air cools, we turn, at last, to the grandest scale of all, the role of heat in the living earth, and the restless sky above. Pause for a moment, if you will, with the warmth of cosmic history still pulsing in your mind, and let the gentle current of thought carry you deeper, past the machinery of engines and the clockwork of molecules, beyond even the grand sweep of stars and the silent arithmetic of entropy. For as we contemplate heat and its restless migration through the world, we come, inevitably, to a threshold where physics dissolves into philosophy, and the flickering candle of human curiosity casts long shadows across the unknown. Consider the air around you now, quietly trembling with invisible motion. Each molecule, bustling ceaselessly, carries a tiny piece of the universe's energy story, a story that began in the searing crucible of the Big Bang and has been unfolding ever since, from galaxy clusters to your own skin. The very warmth you feel in the comfort of your bed is not so different, in essence, from the primordial heat that forged atoms and the gentle radiance that bathes distant worlds. Yet for all its ubiquity, heat is a subtle, almost paradoxical phenomenon. It is both a presence and a process, not a substance to be poured or weighed, but a restless redistribution, a shifting pattern of motion and disorder. It slips between boundaries, seeps through walls, and dances from sun to soil to seedling leaf. It is the cause of change, and sometimes the herald of endings. From the earliest days, humans have been enthralled and unsettled by fire, by the heat that quickens life and devours wood. The ancients saw in fire a living spirit, a sacred intermediary between earth and sky. In the glow of hearths and the crackle of torches, they sensed a truth that science, millennia later, would recast in sterner terms, that heat is the restless unmaking of order, the inescapable cost of all transformation. The great puzzle, the one that has haunted thinkers from Heraclitus to Clausius, is why heat behaves as it does, why all the world seems condemned to drift from the fresh, taut arrangements of youth toward a more formless, featureless old age. This puzzle is encoded in the second law of thermodynamics, a law at once ironclad and melancholy. In any closed system, entropy never decreases. Energy, though never lost, grows ever less useful, less able to do the work we desire. The universe, it seems, is on an irreversible journey from the hot, ordered, and improbable toward the cold, uniform, and inevitable. But what does this mean for us, for the brief and beautiful patterns of life? For on this pale blue world, for a flicker of time, entropy runs backward. At least it seems so. Every green leaf, every beating heart, every bustling city is a local rebellion against the universal trend. Life gathers sunlight and spins it into intricate webs of complexity. We feed on the sun's energy, storing it in sugars and thoughts, building memory and meaning, striving always for something more. And yet, the rebellion is only local, only temporary. The order we create must be paid for with greater disorder elsewhere. The lush forests and intricate minds we cherish are possible only because our planet is not, in fact, a closed system. We are bathed in the sun's lavish energy, and we radiate our own waste heat into the cold vacuum of space. The Earth is a conduit, a brief island where energy is sorted and spent, where heat is harnessed and then released, always moving, from concentrated brilliance to diffuse oblivion. This strange, almost tragic economy shapes every facet of our existence. The warmth of a sunrise, the flavor of a ripe peach, the surge of a symphony, even the persistence of memory, all are paid for with the currency of increasing entropy. Each act of creation, each moment of life, is a kind of heat engine, drawing order from the world and returning disorder in invisible waves. But let us not rush to despair, for in the flow of heat and the rise of entropy there is also a profound source of meaning, a canvas upon which the drama of existence unfolds. The very fact that life is improbable, that order is fleeting, gives richness to our brief sojourn in the sun. The warmth we feel is proof, not of futility, but of participation in a grand, ancient process, a cosmic dance that stretches from hydrogen clouds to human dreams. Contemplate for a moment the ways in which heat shapes not just the cosmos, but the fabric of our lives. In every breath, a gentle exchange, warm air leaving your lungs, cooler air drawn in, the difference a whisper of entropy. In every meal, the sunlight of past seasons, stored in bonds of sugar and fat, broken apart and scattered as you move and think. The rhythm of sleep and waking, the comfort of a hand, the flush of emotion, all are, at bottom, thermodynamic events, their mystery no less for being so. Even our cultures, our technologies, our aspirations are shaped by the quest to master heat. From the first spark struck from flint to the glowing filaments of city lights, we have been a species of fire makers and heat movers, forever seeking to bend entropy to our will. The steam engine, the electric grid, the digital computer, all are monuments to our ingenuity, our refusal to accept the drift toward disorder without a fight. Yet each advance brings new challenges, new reckonings, the need to dissipate waste heat, to balance consumption with renewal, to find order amid the relentless press of entropy. There is something deeply human in this struggle. We build homes to keep out the cold, cook food to make it safe and savory, design machines to transform fuel into motion and light. At every turn, we are negotiating with the laws of thermodynamics, trading energy for comfort, order for possibility. And always we are haunted by limits, by the impossibility of perfect efficiency, the inevitability of loss. Somewhere in the heart of these limits lies a lesson, both humbling and hopeful. For the laws of heat do not forbid beauty or meaning. They merely remind us that all things come at a cost. The fleeting warmth of a touch, the shared laughter of friends, the slow growth of understanding, these are precious precisely because they are transient, because they are born of energy borrowed from the sun and returned in time to the night. And so we come to deeper questions, the ones that linger long after the fires have burned down and the equations have faded from the blackboard. If the universe is doomed in the end to a state of maximum entropy, a heat death, a silent expanse of uniform grey, what then of meaning, of purpose, of hope? Does the arrow of time point only toward dissolution, or is there solace to be found in the journey itself? Physicists and philosophers have wrestled with these questions, their answers as varied as the stars. Some see in entropy the ultimate tragedy, a universe that forgets itself, that erases all distinctions, all memories, all life. Others find in the struggle against entropy a source of dignity, a reason to cherish the fragile, fleeting patterns that emerge and fade. Still others, peering into the mathematics, glimpse the possibility of new forms of order, structures that arise for a time from the play of chance and necessity. For all our tools and theories, we remain creatures of warmth and wonder. We are drawn to the glow of campfires and the hush of winter mornings, to the promise of new energy and the comfort of familiar rhythms. We build stories as well as engines, seeking to make sense of the flux around us, to find our place in the great unraveling. In the end, perhaps, our greatest achievement is not to escape entropy, but to weave meaning from its inexorable flow. Even now, as you lie in the soft darkness, your body radiating gentle warmth, your mind adrift on currents of thought, you are part of this story. A participant in the ancient ongoing negotiation between order and disorder, energy and entropy, life and the long, slow cooling of the cosmos. Each heartbeat, each dream, each moment of curiosity is a testament to the improbable, temporary victory of pattern over chaos, of life over the indifferent march of heat. In the hush of night, the philosophical questions stir. Why should the universe be such a place, where order is possible but never permanent? What is the source of time's arrow, that relentless asymmetry that distinguishes past from future, memory from anticipation. The equations of physics, elegant and symmetrical, care nothing for direction. Yet the world we inhabit is full of irreversible events, of setes, pilled milk and growing old, of heat flowing inexorably from warm to cold. Some have sought answers in the initial conditions of the cosmos, in the extraordinary low entropy of the universe's birth. Others look to the quantum realm, where the rules of probability and observation blur the boundaries between what is and what might be. Still others turn inward, finding in the human experience of time, of aging, longing, remembering, a kind of resonance with the cosmic process. Whatever the answer, the interplay of heat and time underlies all that we know and all that we are. The flicker of consciousness, the rise and fall of civilizations, the cycles of stars and planets, all are chapters in the saga of energy-seeking equilibrium, of heat dispersing across the vastness of space. And yet, within this grand trend, islands of local order persist, flourish, and fade, each a miracle of improbability, each a brief defiance of the cosmic tide. It is in these islands that we live and love, create and discover. It is here, in the transient warmth of life, that we find meaning. The study of heat, in the end, is not just a tale of atoms and equations, but a meditation on impermanence, on the value of what cannot last. Each moment becomes precious against the backdrop of entropy, each gesture a flame briefly illuminating the darkness. As we look to the future, to the challenges that await us, a changing climate, the limits of resources, the quest for new sources of energy, we are called to a deeper wisdom. The lessons of thermodynamics are not just technical, but ethical. They ask us to consider the consequences of our actions, the balance between consumption and stewardship, the legacy we leave for those who come after, the heat we release, the order we disrupt, the waste we create. These are not abstract quantities, but real threads in the fabric of the world. And so we return again and again to the fireside, to the warmth that sustains and the questions that beckon. We marvel at the ingenuity of life, at the ways in which cells and systems, societies and civilizations borrow energy, create order, and pass both onward. We ponder the fragility of our triumphs, the need for humility in the face of cosmic law. In the gathering stillness, one might sense the faint echo of future discoveries, the promise of new insights into the nature of heat, the possibility of harnessing energy in ways we can scarcely imagine. Perhaps, somewhere ahead, new forms of order will arise, new rebellions against entropy, new chapters in the story of warmth and wonder. The universe is old, but not yet finished. Its energy still stirs, and so do we. And so, as you drift towards sleep, let your mind linger on the mysteries that heat reveals, on the connections between stars and skin, on the dance of order and disorder, on the enduring human desire to understand and to create. For in the silence between heartbeats, in the warmth shared and the questions asked, we touch the heart of the cosmos itself, a fleeting spark in the deep, slow burn of time. And somewhere, beyond the reach of certainty, the story continues, its embers glowing softly in the dark. As our journey through the gentle dance of heat and energy drifts to a close, like a comet tail fading into the hush of space, may you carry this quiet wonder softly into your dreams. Rest easy beneath the vast cosmos, and when you awaken, return with open hearts for more Dreamtime tales that whisper the secrets of our universe.